geometric optimization, microstructures, mechanical properties, and then finally the perspective and the conclusion. Okay, so a quick reminder about LPBF characteristics. The main good characteristic about LPBF is that you can create complex, customized parts, like you can see here, with a hybrid material made out of lattice and dense parts. So now you, because of the first presentation, you all know what a lattice is. And it has also a specific microstructures due to its ultra-fast cooling that can create columnar grounds along the building direction, fine solidification cells, or high density of dissipation. It could also have better mechanical properties than other conventional processes. So here, for example, I'm comparing the water stress with LMD or forging. Okay, so LPBF we achieve in dense but intermediate size part has been achieved in has an industrial maturity. But like there's still not a lot of study about smaller parts, and this is why I'm doing LPBF of small objects. So for example, there's this article of someone doing 360L walls, just like the one that we just saw before. And we can see that there's grain oriented vertically towards the center, and for the smaller objects, and the 100 dominant texture that we lose with the bigger objects, and there it's more like a 110 dominant texture. So there's a lot of study about 360L for small parts, but when it comes to nickel alloy or Inconel 625, there's a lot less study. So here you have a study where Leary made cylinders, and he showed that there was no influence of the strut diameters and densities. And like we already said, there's no information about the scan strategies in general for this for the small objects. So this is why I'm trying to understand the influence of the strut diameter on geometrical, microstructural, and mechanical properties on Inconel 625 struts from 0.2 millimeters to 2 millimeters. So about my experimental conditions, I used an Inconel 625 powder. So it's a nickel-based alloy with a high resistance at elevated temperatures and a high resistance at corrosion. It has a lot of application like gas turbines or aircraft engines. The machine that I use is a SLM 125HL, and here are the parameters that I have with different range of laser power or different range of scan speed. For the methodology, it's pretty classical. So first I've made this object. So I have my cylinders between two supports. That's why I call it the Parthian geometry. Then I do cross-section or longitudinal section of my part to analyze the strut geometry or the density. I then do, of course, the microstructure with ABSD, and then the characterization with hardness characterization or tensile properties characterization. And all of that with different strut diameters and different scan strategies. So to start my result, I would like to talk a little bit about my scan strategies, because it's really important to understand. So on the top, you can see, so you can see on all the strategies that it's made out of contours. But the difference between the top and the bottom strategy is that the contours are made from the inside towards the outside, and here too, the inside towards the outside, while the contours are made from the outside towards the inside. It may sound simple, but it makes great difference. As you can see here, here you have the deviation between the theoretical diameter and the as manufactured diameter. And you can see that all the strategies with inside out contours has a diameter that is closer to the theoretical diameter. I also want to show that there's mostly less than 10% of deviation. And you also have to understand that all the strategies here are actually made with only one contour. So all the things that you see here is the same strategy. So this is why it's pretty close and there's not really trends between all the strategies. So this gives us information of how to change the offsets to get closer to the theoretical diameter. When it comes to density of struts, it has been quite complicated because, as you can imagine, cylinders have a really big aspect ratio. So when you do like cross section of your cylinders, it's really hard to have like a porosity rate with a little high standard deviation. So for example, here we can see that in general, you have like between 1.5 and 0.5 porosity rates, but there's not particularly trends on strategies. And we actually doing tomography on the porosity of this, on my samples to have like to be able to see the porosity towards the whole samples. So about the microstructures, here's my 1 millimeter free contour outside in cross section. I like to call it my dartboard because like you can see like the little things like to aim for it. And let's just break it apart. And you can see that it's made out of 3 parts. So you have outer rings, or outer ring, which is the interface between object and the powder, which is made of small grains. Then you have the inner ring that is formed by contours and large grains oriented towards the center, and the hatching area with the zone defining by the hatching vectors, but it's not always here. And so you can see here my EBSD for different diameters from 2 millimeters to 0.2 millimeters. And the main thing that you can see here is that you have a 0.01 texture here that is loose at 2 millimeters. You can also see that here you start to see the effects of the strategy, but here because it's only made out of contour, you don't see like an effect of the hatching, for example. When you compare it to longitudinal cross section, it's really close to what we just saw in the before presentation. You can see here like the little grains on the border, for the outer ring, the inner ring, and the hatching zone in the middle. So about the external ring, it has a constant grain size. It doesn't matter if it's of the size of the scan strategy, it's always between 10 and 15 micrometers. And this is due to a constant cooling conditions near the powder. For the inner ring, it's a little bit different. We can see that you have with the biggest struts, you have the grains that become like with a bigger diameters. So as you can see it here, and it makes us understand that the grain size is due to the juxtaposition of the contour. And also like with the biggest struts, you have the temperature, the average temperature in our cylinders are higher. And so it makes like bigger grains. When I also wanted to study the outer ring length, because I realized that between the out-in and in-out strategies, you can see that the outer ring can have like different length. And so this can be connected to the first result that we see just before. And it makes us understand that the crown, the outer ring, corresponds to a zone melted only once. And so about mechanical properties, I'll be fast on that. I found like something really interesting about the hardness. So here we are in a 2 millimeters cylinder with 3 contours outside in and with hatching. You can see that the hardness is between 320 and 270. But what is interesting is that the hardness is higher in the zone that we just saw before, the inner ring, which is a bit odd because you have here bigger grains. So we're trying to understand that, and we have an idea of maybe it's because of maybe there's more dislocation on the site, but it's still ongoing studies. And you can see also that the average hardness for the struts like increase with the diameter is yeah. And when it comes to the tensile tests, You see also, once again, the difference between the two strategies, outside in here, inside out here, and you have like the best mechanical properties for the outside in strategies, where you have lower, and you have lower tensile resistance for the inside out strategies. So maybe it can be due for different porosity rates, different between the strategies, or once again, the dislocation density. So I would like to, can you maybe after, it's a video, but not yet. So I would like to explain a little bit about what we're going in the future. So like I said, we have to work on the dislocations to better understand the mechanical properties and the evolution of the dislocation density in the same samples. And we also are developing at the moment a fast imaging LPBF machine. So we can do in situ characterization of the size of the melt pool. And so you can see here a video that is here. And so from here, we can like see how the melt pool increase. It's to understand the relation between the morphology and the grain size and the melt pools with the melt pools. And we're also running some simulation on thermal behavior to compare it with what we're having here. And so to conclude, there's a few things that I wanted to explain. So there are different size of struts can have an effect on the geometry or on the grain size. Also, I wanted to say that the scan strategy can have a big impact on your geometric, on your tensile properties or the localization of the geometry of the grains. And there's a relation between microstructures and mechanical properties, like we saw with the hardness results. And finally, the average temperature and the thermal conditions have an impact on the grain size. So thank you very much for your attention. Do you have any questions?